Assalamu alaikum. How are you doing, guys? Today I'm going to talk about matrices and matrix operations. Well, when you have a lot of data, you like to sort it out. You like to summarize it in a table that will help you to deal with. For example, when I record your grades, I do that in an Excel sheet where I put, for example, the names, and I put quiz number one, quiz number two, test number one, test number two, and so on and so forth. So what I get here, I get columns and I get rows, correct? The columns are the rows are your names, and the columns, they are your assessments. Okay, so when we put it in this way, it will help us to deal with it. Okay, here in mathematics, when we put some data in a table, we call that a matrix. So today we are going to talk about matrices, and we are going to develop certain operations, or we are going to develop ways to deal with matrices, so we can define algebraic properties, we can define operations on matrices, and that will help us to utilize them and do something related to linear systems in particular, and do many other things in general. Okay, so what do we mean by a matrix? A matrix basically is a table of data. You put it in this way. A matrix is something like this: A11, A12, A1n, A21, A31, AM1, here A22, AM2, and you keep going, A2n, and here AMN. So how many rows do we have? We have M rows. So this is row number one. Row number one. This is row number two. And so on. If you think about this, this is column number one. This is column number two. This is column number n. So how many columns do we have? We have n columns. So we have m rows, n columns. So we call this matrix A is an m by n matrix. Okay, so we identify the matrix, or when we say a matrix, we have to say the size of that matrix using the number of rows and the number of columns. Look, M goes for the rows, N goes for the columns. Okay, and that's standard. So whenever I say M by N, I mean here we have M rows and we have N columns. Okay, from now till forever, that's what we write and that's what we do. Now, we need to identify the elements in your matrix. And we identify the elements based on their locations. So, for example, when I say here the element 822, I mean the entry in the second column, second row. Okay? When I say here A31, I mean the entry in the third row, first column. Okay? So sometimes we need to describe certain entries in that matrix, and you can do that by giving which row, which column. Okay, and that is natural. I mean, if you are dealing with an Excel sheet and you want to describe certain cell, you can say the cell in row so and so and in column so and so, and that will specify which cell you are talking about. Okay, so here the entries in your matrix, they are like cells in your matrix sheet. Okay. So that is just a very simple way to describe your matrix and the elements of your matrix. What we need to know now is how to do algebraic operations here. And the first thing is how to add or subtract two matrices. How to multiply a matrix by a number. We have to multiply two matrices. Well, let's think about the answer to these three questions. Always when you want to define a new operation like addition or subtraction or multiplication, you need to define it in a way that makes sense and that is helpful, okay? It doesn't make sense to define something that is not helpful or that is not usable, okay? You can define multiplication or addition in any way you want, but the question, does it make sense? The question, is this going to be helpful or usable in something else? Okay, and here when it comes to matrices, we need to define addition, subtraction, multiplication in a way that is helpful and that makes sense. Well, the answer to the first question, addition and subtraction of matrices, that's very easy. All you need here is two matrices of same size, okay? So here, if your matrix A is, let's say, A11, A12, A13, A21, A22, A23, A31, A32, A33. And your matrix B is 1, 2, 3, 4, 5, 6, 7, 8, 9. So this matrix is a 3 by 3. This matrix is a 3 by 3. So addition or subtraction, that is very easy. You add or subtract component-wise. So that is going to be what? That is going to be A11 plus or minus 1. Well, let me take one of them. The other will be similar instead of confusing you. So that is plus 1, A12 plus 2, A13 plus 3, and here A21 plus 2, A22 plus 3, A23 plus 4. This is A31 plus 1, A32 plus 2, A33 plus, 1, 2, 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9. So we add component-wise. Similarly, if we want to subtract. So addition and subtraction, that's a piece of cake, okay? You need your matrices to be of same size. If your matrices don't have same size, you cannot add them. It doesn't make sense to add them if they are of different size. So it's like adding orange to apples. Can we add orange to apples? Yeah, you can. Or can you compare orange with apples? We always say don't compare orange with apples, correct? All right, adding and subtracting matrices, that's very simple. The question is, okay, how to multiply a matrix by a constant? That's also easy. So here the answer to question number 1, here it is. The answer to question number 2, here it is. If you multiply the matrix B by a constant, you multiply each entry in that matrix by the same constant. So in this case, what you get? You get here K, 2K, 3K, 4K, 5K, 6K, 7K, 8K, 9K. So again, multiplying by a constant, that's easy because you multiply each entry of that matrix by the same constant, okay? So whenever you want to multiply, you can do it, and whenever you want to factor K out, you can do it, okay? So here, if you have a matrix like this and you want to factor certain constant or certain number out, you can do that, okay? All right, let's come to the third question, which is more interesting. How do we multiply two matrices? Should we multiply component-wise as we did in the addition? Well, remember what I said. We want our operation to make sense, and we want that to be helpful and usable. Okay? So if I go back to your first grade math, and I tell you here, what does it mean when you say here 3 times 2? Do you remember how you multiply that? Yeah, it is 6, but how did you learn that? You learned that as 3 groups of 2 elements each, correct? So 2 elements in 3 groups, and you count them, you get 6, correct? So here, how do we do multiplication here? Well, let's start by something simple, which is when we have a matrix and we have another column matrix, something like this. I don't want to write the general case. I want to write just something simple here. Okay? I want to write the matrix A, and I want to multiply that by another matrix. Let me call it C here, and or V, and this I'm going to take it x1, x2, x3. So AV, this is going to be this matrix multiplied by this matrix. We want to define that in this way. So here is A11, A12, A13, A21, A22, A23, A31, A32, A33, and this is multiplied by x1, x2, x3. This is how we want to multiply. We multiply this by this component-wise. We get A11, x1, then you add it to A12, x2, then you add it to A13, x3. So from the first row, you multiply it by this column. You get this. Look, this is going to be a number. I mean, you multiply, you add, what do you get? You get a number. Okay? Now, similarly here, you get A21, x1, plus A22, x2, plus A23, x3. And here you get A31, x1, plus A32, x2, plus A33, x3. This by this, this by this. That is what you get here, that is what you get here, and that is what you get here. So this matrix, it was 3 by 3. This, it is a 3 by 1. What did we get here? We get a column matrix, a matrix that has one column, which is 3 by 1. 3 by 3, 3 by 1, we got 3 by 1. Okay? Again, why do we do that? Because that is going to be helpful to us. Okay? If you like to take it with numbers, replace A11, A12, A13 by numbers and do the computations. So you get here the answer. Okay? So from here, if you want to generalize this, you can see the elements in your row, the number of elements in your row should be the same as the number of elements in your column, which means what you have here should be the same as what you have here. Again here, if you want to do what I did here in general, it means you need this is m by n, and you want to multiply it by another matrix that has one column, this has to be n by 1. Look, this has to be the same as this. So in that case, what you get here is going to be something of size m by 1. Let me give you a specific example before I generalize this. So here is our matrix A. 1, 2, 3, 4, 5, 6. This matrix is 3 by 2, correct? Or 2 by 3? 2 by 3. Let's take this matrix V equals 1, negative 1, 1. So what is AV? AV is going to be 1, 2, 3, 4, 5, 6. Here, 1, negative 1, 1. When you multiply this by this, you get 1 minus 2 plus 3. Here you get 4 minus 5 plus 6, and that is 4 minus 2 is 2, and here is 5, correct? That is what you get. So this is 2 by 3. This is 3 by 1. This is 2 by 1. Okay? So now, if we have a matrix m by n, and we have another matrix n by 1, we know, or we can do the multiplication in this way. We know how to do it and get the answer. The question is, if we have something that is more general. Well, the idea here is easy to generalize. If we have a matrix here multiplied by a matrix here, then for sure you have columns here. You have columns here. And you have rows here. So now we can think about this idea in general. I can think about doing this on this column, then this on this column, then this on this column. So now I can handle the general case as we did here, but do the multiplication of this matrix by this column, then by this column, then by this column, and so on and so forth. Okay? So from here you can see something. You can see that if this matrix is m by n, then you want here the same number of elements as those in this column. So here you need B11, B21, up to Bn1. Look. So if this is m by n, then certainly you need this to be n by something. Okay. So here, it doesn't matter how many columns you have. That's fine. The important thing is you need to have the number of rows here to be the same as the number of columns here. Okay? And in that case, you can do what we did here for each one of those columns. Okay? And in this case, you are going to get, look, do this on this, you are going to get the first column. Do this on this, you are going to get the second column. Do this on all columns, you get the columns here. So, what are we getting here? We are getting here this is m by n, this is n by k, we are getting here m by k. Because what you get here is going to be coming from the rows here, and that is, how many rows do we have? We have here m, so this is C11, C21, CM1. Okay, then you keep going in the same way, here, 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 and in that case, you get a matrix. It is m by k. Okay, so that is how we should do it in general, and now I'm ready to give you a specific example. So let's do this example. A equals 1, 2, 3, 4, 5, 6, and B equals 1, negative 1, 0, 0, 1, negative 1, 1, negative 1, 0. This matrix is 2 by 3. This matrix is a 3 by 3. So find A, B. Or can you find A, B? Well, 2 by 3, 3 by 3, according to our way of doing it, yes, we can do that. Okay, so how do we do that? Here is A, 1, 2, 3, 4, 5, 6, and we write here 1, negative 1, 0, 0, 1, negative 1, 1, negative 1, 0, and now we multiply. Look here, I'm doing that slowly, but after a while, you can do this very fast, okay? So you multiply this by this. So 1 times 1, 1, 0, 3, so you get 4 here. Now, this by this will give you 4, 0, 6, that is 10. Done. Now, you go to this one. This multiplied by this, you get negative 1 plus 2, 1, 1 minus 3, negative 2. Now, this by this, negative 4, negative 4 plus 5, 1, 1 minus 6 minus 5. Now, again, you repeat yourself here. 0, negative 2. Now, here, 0, negative 5, 0, that is negative 5. So, 2 by 3, 3 by 3. What did we get here? 2 by 3. Okay? All right, here's my question to you. If I asked you, instead of find AB, I ask you, can you find BA? BA, is that possible? So here, what about B, A? And I'm talking about that B, that A. So B here is, as you have it there, it is a 3 by 3. A here is 2 by 3. Can you do that? Not possible. Because this is different from this, not possible. So from here, you can say AB is not the same as BA. And that's something you are not used to do in numbers. In numbers, AB is the same as BA. So from now on, when you have matrices, don't tell me AB equals BA. So the order is important here, okay? If I find that you are mixing them, well, it means you don't know what you are doing, okay? You cannot, unless there is something to guarantee that AB is the same as BA, okay? So matrix multiplication is not commutative in general, okay? Keep that in mind, please. All right. When your matrix is F, the matrix A is n by n, we say A is a square matrix. So when number of rows is the same as number of columns, we say the matrix is a square matrix, okay? Because it's like square. Number of rows is the same as number of columns. And in that case, you can multiply the matrix by itself. In that case, it makes sense to say here A squared equals A multiplied by A. I don't need to write multiplication sign. A cubed is A multiplied by A multiplied by A. And in that case, you can multiply in the same way, but you can keep doing it, okay? In general, you can say A exponent K for whatever K you have, as long as it is positive integer here, okay? So you can take here a matrix that is 2 by 2, and as a practice, you can multiply the matrix by itself, multiply it by itself again, multiply it by itself again. By the way, that is something interesting. We are going to deal with it later on. So later on, we are going to take square matrices, and we are going to find or evaluate that matrix to high exponents, okay? All right. There is something here called the transpose of a matrix. The transpose of the matrix. The transpose of a matrix, you make the columns rows and the rows columns. What does that mean? So if you have a matrix A equals A11, A12, A1n, AN1, A21, A22, A2n, and here AM1, AM2, AMN. A transpose is the first row becomes first column here. So A11, A12, A1n. The second row becomes second column here. A2, 1, A2, 2, A2, n. And so on and so forth. So the transpose of A, you just change the rows into columns, okay? All right, let's take example here, and I'm going to keep the same A here. A transpose is 1, 2, 3, 4, 5, 6. That's it. That is the transpose of A. We have another concept that we need to deal with. It is called the trace of a matrix, and that is related to square matrices. If you have a square matrix, so it means M is the same as N. In that case, let me write it here. If A is a square matrix, trace of A is defined to be A11, plus A, 2, 2, up to A in N. So what do you do here? You take the elements along the diagonal. This is called diagonal. So here M is the same as N. So you take those elements along the diagonal and you add them. You add them. So what you get here, you get a number. So the trace of a matrix here is a number that is associated with your square matrix. Okay, so we have the trace, we have the transpose, and we have matrix multiplication, we have matrix addition, we have matrix subtraction, and we have multiplying a matrix by scalar or by constant. Let's take one example here. Example. Let me take here let A be this matrix, -1, 0, 1, 3, 2, 4, and this matrix B is -1, 1, 2, 3, 4, 1, 4. And here is the question. The question, can you evaluate 1, A plus B, 2, A minus 3B, 3, A, B transpose, 4, trace A, B transpose, and here let me just draw this one, A transpose B. We have two matrices, and we are asking you to compute, if possible, those. Well, let's do it. Well, this is a very simple question, but since this is our first class about matrix multiplication, so let's do it step by step. But later on, you are going to find this is just a piece of cake, okay? All right, so here number 1. Can we add? Well, we need them to be of same size. This is 2 by 3. This is 2 by 3. So yes, we can add them. So basically this one and this one, yes, we can do it. So let's do it. A plus B is -1, -1, that is -2. 0 plus 1, that is 1. Here 3. Here 7, here 3, and here 8. Please double check. 2, A minus 3B, that is going to be -1 plus 3, that is 2, 0 minus 3, 1 minus 6, that is -5, and 3 minus 12, that is -9, then 2 minus 3, that is -1, then 4 minus 12, that is -8. Please double check again. Double check. 3. Okay, A, B transpose. What is B transpose? B transpose. So let's first do B transpose. B transpose is -1, 1, 2, 4, 1, 4. Now, can you do A, B transpose? Can you? Look at it. This multiplied by this, that is possible. 2 by 3, this is a 3 by 2. So 3 columns, 3 rows. So yes, we can do that. Okay, so here, this is going to be let me write it, negative 1, 0, 1. Here, 3, 2, 4. And here, negative 1, 4, 1, 1, 2, 4. And now you do the multiplication here. Again, as I said, once you practice few exercises, this is going to be fast and easy. Okay, so let's do it together. So this multiplied by this, it will be 1 plus 0 plus 2, that is 3. This multiplied by this, it will be negative 3 plus 2, negative 1, negative 1 plus 8, 7. Now, this multiplied by this, negative 4, 0, 4, that is 0. And this will be 12, 12 plus 2, 14, 14 plus 16, that is 30. So this is 2 by 3, this is 3 by 2, this is 2 by 2. Double check that, please. So this multiplied by this, we got a 2 by 2 matrix. Here it is. Okay, so we're done with this, we're done with this, we're done with this. What about the trace of AP transpose? It means it is going to be the trace of this. And what is the trace of this? You add the elements along the diagonal. So now, for trace AP transpose, for trace we write TR. And sometimes I write it T small, sometimes T capital. It depends on my mood. But whether it's T capital or T small, it's the same. Okay? We mean by that the trace. And this T here, we mean by that the transpose. Again, it's possible to see this T capital, this T small, so don't worry about it. Okay. That is 3 plus 30, which is 33. Okay? Now, what about A transpose B? Can we do that? A transpose, it is going to be, so here, 5. A transpose is going to be negative 1, 0, 1, 3, 2, 4. Now, A transpose B is going to be negative 1, 3, 0, 2, 1, 4, and B is negative 1, 1, 2. Here, 4, 1, 4, and 1, 1, 2, 4, 1, 4. So now, can you multiply? This is 3 by 2. This is 2 by 3. This is the same as this. So yes, you can multiply, correct? And when you multiply, what do you get? You are going to get this time a 3 by 3 matrix. So let's see. You start this by this. 1 plus 12, 13. Now, this by this. You get 0, you get 8. And this by this. You get negative 1 plus 16, that is 15. Now, you repeat yourself with this column. So what do you get? Negative 1 plus 3, that is 2. This times this, you get 2. This times this, 1 plus 4, that is 5. Okay. Now here, negative 2 plus 12, that is 10. And here, 0, 8. And here, 2 plus 16, 18. So this is A transpose multiplied by B. This is what you get. Can we ask you about the trace of that? So here, if I add another question, 6, trace of A transpose B. Yes, it's a square matrix, and in that case, it's going to be 13 plus 2 plus 18. That is 33. Okay? Now, you can see here the answer is 33, and the answer here is 33. Does that mean Does that mean it is a coincidence, or that is coming as something valid in general? Look. That's interesting. This matrix is 3 by 3. This matrix here is 2 by 2. But we got 33 here, we got 33 here. Is that coincidence? Well, think about it. Keep it in your mind. Or maybe you can try one more example or a couple of examples and keep it in your mind. We're going to come back to that. Okay? We're going to come back to some properties of the trees and see, is that valid in general, or is it just coincidence? Okay? All right. I'm not going to answer the question, so I'll leave it open for you to think about it. Okay? Later on, we're going to talk more about the trees, and I will remind you about the question and see whether you got a conclusion about it or not. All right. One final thing here. Let me talk about that. What is the relationship between this and between linear systems? Remember, this course is about linear systems, and everything we do, it is going to relate to linear systems. Everything we do, we're going to come back and apply it to linear systems. Okay? So here, when we say here, a linear system like 2x1 minus 3x2 plus 4x3 equals 1, and x1 plus x2 plus x3 equals negative 1, and 3x1 minus 2x2 plus x3 equals 4. How does this relate to what we did here? Well, we can write this linear system in matrix form as follows. I can write the coefficient matrix 2, negative 3, 4, 1, 1, 1, 3, negative 2, 1. Then here I can write a column matrix for the unknowns. And I can write here a column matrix for this part. Let's see. If we do the multiplication as we did here, you have this multiplied by this. So what do you get? You get this. So equals this. Then this multiplied by this, you get this equals negative 1. Then this multiplied by this column, you get this equals 4. So we can write this linear system in this matrix form. And if I write this as A, and I write the unknowns as X, and I write this as B, I can put this system in this nice compact form as AX equals B. So this is my X, this is my A, this is my X, capital X, and this is my matrix B. So AX equals B. That is my linear system. So from now on, it is possible that we write our linear system in matrix notation as AX equals B. Okay? A is the coefficient matrix, X is the matrix of the unknowns, which is column matrix, and B is the non-homogeneous part, or what you have on this constant term here, or terms. Okay? And once you write it like this, you can see that what we got here about addition, multiplication can be utilized here, and we can do something interesting here. Okay, so I'll leave that for the coming lectures, and I'll stop here. Thank you, guys. Please practice exercises about matrix multiplications. Okay, you need to be able to do it in no time. It shouldn't take you forever to multiply two matrices. Okay, I did it here kind of slow, step by step, but we need to do it fast. When we multiply two matrices, we have to do it fast. So please practice some exercises about it. All right, thank you, guys.